Thank you. Okay, our next speaker is presenting over Zoom, Danna Gurari from the University of Colorado Boulder on AI descriptions of visual content taken by people with visual impairments. Danna, can you hear us?
I can hear you. Can you hear me?
Yes, we sure can. Take it away.
Wonderful. So it's a pleasure to be here. I am an assistant professor at University of Colorado Boulder in the computer science department, and I am super excited to share about our work in this realm. And so the goal for what I'm going to share is to teach computers to automatically describe images taken by people with vision impairments. My inspiration for this work started when I was a postdoc almost 10 years ago now, and I was told that there's this new problem called visual question answering that came out. And it was a very toy problem when it came out, and I wanted to work with real people's data. And so I discovered that there was a real data set that existed where it was collected by an individual named Jeffrey Bingham, where he had built this app that let someone take a picture with their mobile phone, which would then be sent off to the cloud with potentially a question about that image. And then remote individuals would be able to provide an answer. Originally, it was my colleague, Jeff. Eventually, it became crowd workers on various crowdsourcing platforms. And those individuals would return either a description of that image or an answer to the question. And so I was really excited when I discovered this data set. It had been used by 11,045 people who submitted 72,205 requests from 2011 to 2015. I started my postdoc in 2015, right when this app ended. And the really cool thing that happened was that there was a clause that people could sign off on that they would be willing to share their data for research purposes. And so my team ended up getting in 2015, around that time, 62% of the requests for which users agreed to share their data. And that was 44,799 of these submitted requests. I show on this slide some examples of what was submitted by the users of this application. There's questions like, do these clothes look dirty? What flavor is this? What types of pills are these? Please describe what you can see. Since then, I'm guessing, I'm not sure actually in the audience who's familiar with the different technologies that are out there, but there have been many technologies that provide similar capabilities that have emerged from Microsoft seeing AI. Apple now has built-in utilities within their phone. Google Lookout, Be My Eyes connects you with remote humans so you can have a dialogue. There is the automated app Tap Tap See, Orcam, Envision, the list goes on. But while this is super exciting, and I'm very excited about this, and I actually talk with individuals from many of these companies, what I think is the concern for our community is that we don't have access to any of that data. None of that data is publicly shared, and for very good reasons. Basically, that means that it creates a barrier for individuals who want to do research in this realm. And so in this talk, what I'm going to share is about my team's work and how we were able to put out the first AI challenges that do enable a broader research community to develop models to analyze images taken by visually impaired photographers. And then I want to kind of set the stage for where I think the field should go and perhaps is already starting to take steps in that direction. So diving in first to the AI challenges coming from my team, the way that progress works in my little niche of the research community, which is not such a small community, I'm part of the computer vision community, and that's basically our conferences attract over 10,000 people every year for the past few years. A lot of how progress is monitored is we come up with some sort of test that we have algorithms compete on, and then we say which ones are the leaders. And so an example that was discussed in Miguel's talk, I think, was ImageNet. So what our team has done is the same thing. We've created these AI challenges, which are basically saying, here's a test, algorithm, please provide the answer. And we have these answers that are hidden. You can submit your answers, and we will once a year announce who are the winning teams and ranking of first, second, third, and so on order. And so that's what we have done. And the inception for these challenges was going through and making this repository of data we got from real end users of a visual assistance technology to make it available for the public. And this is a non-trivial effort when you're dealing with real people's data. The first step we did was we anonymized the data, which involved transcribing the questions to remove people's voices, and we resaved images to remove any kind of metadata. We then went through every single one of the images multiple times to ensure there's no personally identifiable information in any of the data we shared. We found things like faces, prescription pills, mail, and more. And finally, we went to typically a crowdsourcing platform called Amazon Mechanical Turk to label our data to support different kinds of tasks. In total, over nearly the past decade, we have put out 13 AI challenges around this data. The contributors of this work have consisted of the initial thousands of VisWiz application users. We've had thousands of Amazon Mechanical Turk crowd workers who have given over 5,000 person hours to annotate the data. This is equivalent to several years of 40-hour work weeks if you had a single person doing this. There have been 19 students who have contributed and 6 collaborators. And I'm just going to preview some of the tasks that we've put out there for the AI community to compete on in developing models. One, hearkening back to the previous talk from Frank, is this idea of image quality issues. So we saw there were many image quality issues of varying severity. Things could happen like you could not even recognize the content. I showed an example on the left. Other times, maybe you could recognize the content, but there are other kinds of issues, such as the image was blurry. It was too bright or oversaturated, or too dark, undersaturated. Maybe the framing wasn't quite right. In this case, you see most of the framing is on the hand, and there's a little bit of a frame on a bottle that one would imagine the person wanted to actually learn about. There can be obfuscations. It seems like someone's finger is partially covering the camera, but then you can see in the hand what appears to be a coin. And then maybe there's some rotation issues where it might be hard for a human observer to quickly pick out, because a bag is upside down, that there's a walker's bag of potato chips. When we went through and we labeled the data, we found that roughly half had some kind of quality issues. Pretty amazing that half actually didn't have any quality issues, because of the fact that these are people who are blind, so couldn't verify what was the quality of the images they were using. And then I showed just kind of the distribution below the examples I have of what percentage of images had each of the flags. Blurry was the most common, arising for 41% of the images. Obfuscation, also improper training was very common with 55.6 images. And obfuscation was only for 3.6% of the images. So we had varying prevalence of these kinds of issues, but they all happened. And so we put out a challenge to predict, can you recognize what's in the image or not? And can you predict what are the quality flaws that are arising from those that I articulated? Just a note, if anyone is interested in going deeper, I put in the bottom right of each slide where the publication is that describes this work. I'm going to just fly through all these, but each of these have a publication that really go into detail on all of them. The next follow-up work on assessing image quality was we also did some assessment on the image subregions. So not just saying overall what's going on with the image, but maybe we can find within an image where these different flaws are. Maybe you have, for example, a location that's really bright in one area and blurry in other areas. And so maybe you can imagine predicting where those areas are and having some post-correction being done if you could predict those regions where these issues arise. Another task that we did, which again relates to some work that Frank just discussed, is just recognizing the content in the images. And Frank's talk, he introduced this data set called Image C, which has these image corruptions that are put on the images. What we noticed is that the existing data sets that support this kind of analysis of how robust are algorithms when they encounter image corruptions is that existing data sets all had manipulated images to induce a corruption. So these weren't naturally arising. They were all fakely introduced through different kinds of image manipulation methods. So what we said is, let's go ahead and do some robustness testing for models on the categories that are available for ImageNet using the images in our data set. So we went through and we labeled 8,900 images where these categories of interest occurred for 200 object categories found in ImageNet. So we could then say, how do these models do when applied to this VisWiz data set that have naturally occurring corruptions? We found they don't do very well. So now this challenge is available for the community to continue trying to improve upon the models. We also have introduced tasks around locating the content in images. And so what I show here is an example of one of those data sets we put out, where we have in 4,500 images, so a very small number of images. We labeled the presence or absence of 100 categories, resulting in about 10,000 segmentations. Categories spanned microphones, hats, remote controls, broccoli, ramen, gift cards, receipts, flash drives, people, forks, wallets, watches. We put out another challenge, which says, maybe don't look for specific categories. Why not instead look for the most salient object? Because typically when someone took a picture of something, they wanted to learn about that object. So we don't need to know what the category is. We just need to find the object so we can start to describe that most prominent object that's in the image. So we did this for 32,000 images, where we actually segmented the foreground or the most prominent object in the image in all those images. And we have a challenge that's out on this particular task as well. Another task we have was locating the content in images for private categories. I mentioned when we built the data set, we found a lot of private content in these images, and those occurred for both because people wanted to capture that private content in images, but also because they didn't intend to, and it just appeared somewhere maybe in the background. It was unintentional. And so we built another challenge where we went through all the images with private content, and we actually we obfuscated that content, and we inpainted in different ways. But we built a challenge that says, can you predict where private content would be in these images from the context? Because we, of course, weren't going to release the private content itself. So given an image, try to predict whether or not there's private content and where it's located. Our final round of tasks that I want to highlight are around describing images, which was the original motivation in creating this data set. So given an image such as this one, either provide some kind of description, what we call a caption, often in our computer vision community, such as a bunch of small light brown mushrooms in a green field, or answer a question about the image, such as, is it edible or poisonous, where the machine should answer poisonous. I'd like to highlight that this is the first set of public data sets for these two tasks that actually originated from an authentic use case. So all other ones were made up, just downloading images often from the internet and having people just describe those images or make up questions that they think are interesting. So this really represented, what do real end users of these kinds of systems want to learn from an image? One of the tasks that we introduced, one of the follow-up tasks that we introduced was also to determine whether a question can be answered or not. Here I show an image where the question is, what is the expiration date? You can't see on this carton of coffee creamer where it is. It's out of the view. And so in this case, the answer should be unanswerable. So that was another challenge we made. In our data set, we found that 29% of 31,173 visual questions had the situation where the question cannot be answered. As I mentioned, there's a lot of private data in this data set. This was in part because people found that that was the best avenue they had many times to learn about that private content itself. We found that 1 out of every 40 submitted visual questions had private content in the image. And for 62% of those images where there were questions about them, the questions actually asked about the private content, because that was the best that perhaps the user could do to learn about, am I, for example, taking the right medicine when I open up a pill bottle? So in the example I show here, the question is, what is the medicine in this pill bottle? So we have another task, which is indicating whether or not someone's asking about the private content, so we can let those kind of questions through in theory. That's just a highlight of the different challenges we've had. We have, like I said, hosted an annual workshop where we announce the winners for a wide array of these challenges that we've created. We've had, over the past 5 editions of this workshop, over 120 teams who have competed. They have come from both academia and industry, which is wonderful because it can help with translational research into actual end products. These challenges have been difficult for a number of reasons for modern algorithms, including because many images are lower quality. Also, because many contain text in them that was atypical at the time that we released this data to the public. Also, they contain many novel concepts, kind of like what was showed in the unsupervised learning talk, the second talk that we saw. You imagine strapping on a camera onto a child's head and seeing what do they see. This is kind of the situation where you have people who are blind who are taking pictures. This doesn't reflect what the community was doing in the past to curate images. What the community often wanted to know from our audience, and 47% of submitted images, was about the actual text within images. And so that was something that we helped the community adapt and start developing algorithms for. And then the last challenge from our data sets is that because we're working from data from real users, we have much less data than is possible when you contrive data. So as a result, many of our challenges are predicated on having a relatively small amount of data to train models, whether that's, in the span of like 10 or 20,000 examples, which is relatively small in our community, to some challenges where, because of how we have to filter down the data set, we provide maybe 10 examples for training. So basically models have to learn how to predict when they have such a small amount of data available to them. Excitingly, we have found that AI can now exceed human performance for captioning images, answering visual questions, and finding salient objects. On our dataset challenges, there's still much to follow. So before I highlight those, I just want to do a shout out on what has already been discussed in the previous talks, which is what is today the state of the art. We have seen kind of a progression on the kind of models we heard in this talk, where people were starting out with CNNs and RNNs of different kinds of flavors and putting those together to do predictions. That's kind of what we found was the earlier set of models. Today, across the board, state-of-the-art models are going to be what are called transformers, which basically embed billions of parameters. Some people say even you have in things like ChatGPT trillions of parameters. So basically these networks that just have lots and lots of connections that are trained on massive amounts of data. Think about pretty much all the data on the web, going and crawling those web images. Often there are descriptions paired with those images. So just basically crawling the web and figuring out how do we consume and feed into these neural network architectures that data. That's basically what we have as the state-of-the-art models across the board for these different tasks. And often there might be some kind of fine-tuning stage to adapt them to the specific tasks that we have. I invite everyone to come and explore the labeled data sets. We have a browser that we publicly share at viswiz.org, where you can actually browse through different examples. You can search for things based on the visual question. You can look for things in the answers to visual questions. You can search for things in the captions, and much, much more, also on quality issues. So if you want to actually look at the data, feel free to come onto viswiz.org and check it out. I also invite you to join our AI challenges. We every year are putting out new ones. I just had a meeting yesterday where we talked about what's going to happen in 2024 for our challenges, but we have a list of the available challenges on our website. And we also host an annual workshop every June. And so I invite you to that as well. James Coughlin actually was a speaker at one of those. And so perhaps we'll invite one of you as well to come and give a talk there. So I would like to end now with talking about where I envision the field needing to go. One thing we have actually heard from, I think, every single talk beforehand, which is how are these models making decisions? And similarly, my team has observed that there's an issue that they're not making decisions based on the evidence that is in the images, but rather based on some kind of bias. So imagine crawling the web, maybe most of the bananas show yellow bananas. So when a models ask what color is the banana, it'll answer yellow. We benchmarked our visual question answering models that are state of the art to figure out, are they looking at the correct visual evidence when they predict the answer? And what we found is that for at least 70% of the visual questions, AI models do not look at the appropriate evidence when they predict the answer. This is even true when they are predicting the correct answer, such as, is this shampoo or conditioner? I show where the ground truth evidence is in the image for where you would find the answer is shampoo, but the predicted answer also says shampoo while looking at the entirely wrong area in the image. So that's an issue that for sure needs to be addressed, that I'm the fourth speaker to mention. Which intelligence should we embed in AI models? Well, it sounds very clear cut when you present a challenge and you say, here's the test, algorithms go provide responses. What you find is that humans are not so black and white. You can have humans provide different answers to visual questions, such as which is the recycling bin? And you see an image showing two different bins in what appears to be a garage. Some people might say on the right, some people might say closest to garage door, some people might say green, can on right. There's different ways of having an answer, and figuring out what is the right kind of information to convey to an end user, I think, is an important question. And it might be that you want to convey everything that you might hear from a crowd. This is also true for captioning images. I show here an image that has been captioned by 5 different people, saying a dog is in the front yard of a house, a shot of a front yard with trimmed grass and some bushes and the road visible. Pictured as a front yard facing toward the street in front of a house. Hopefully you get the idea that different people are automatically thinking of different kinds of information to provide. And there's a question of what should be in a description that we give to an end user. And maybe this should also be personalized to different users and results that they want. And the final key challenge that I'd like to highlight is, how do we go about designing privacy-preserving AI models? As I mentioned, people who are blind are often using these services to learn about their private content. We can't ignore this. And so I think we need to start building models that can be run on devices to support the users with those about 10% of submitted images that are showing private content. And so I would argue that we need solutions that can learn from none or a few examples, which is called zero or few shot learning, to detect different private categories, because we never want to build a big data set of private content by definition that shouldn't be publicly available. And we want these models to be compact so they can run on device, so that we are not having people sharing their information with someone else. They're doing everything on their own device. And so another key important area is also developing compact models, which goes against what transformers are, which is these billions to trillions of parameters sized models. So with that, there are many people to acknowledge. I've already mentioned that I have had many mentees working on this, many colleagues. There's people who have actually supported these VizWiz dataset challenges in both designing the application and crowdsourcing. We've been funded by NSF, Microsoft, Adobe, Amazon to contribute to this work. And so if you want to get involved, I encourage you to visit vizwiz.org. Everything I've talked about and more is on this page. You can, from this page, learn more about technological needs of blind people by browsing the data set. You can join a VizWiz challenge to design algorithms for blind people's data. You can deploy these inclusive algorithms for the benefit of society. You can also join our community by coming to our annual workshop. And so with that, I welcome any questions.
Thank you, Danna. Do we have any questions from the audience? Sometimes it takes a minute. I have one, and this may actually bleed a little into a potential discussion topic. We're talking about these huge models that can classify almost anything, but we have this in 2 ways of wanting to learn about the visual system, what we heard in the second talk about biophysical constraints on those networks. And you're also talking about compact networks so that we can preserve privacy and run things on folks' devices. How does all of this come together, almost even ethically? Like, do we get into a state where we should be constraining how we do this, both for privacy and so that maybe these networks don't get smarter than what we're capable of and seeing things we can't see? I'm like thinking of those fundus images where you can tell somebody's gender, but nobody who looks at fundus images can do that. I don't know, just a curiosity. You brought some of these elements in, Danna, so I'm super curious if you've sort of wrestled with this question at all.
Yeah, so I think I heard about 3 questions in there, so I'm going to make sure I'm not. So I think one of them is like, how do we unify the different worlds? So we've heard different talks. 3 of the talks really talked about really understanding more of the brain and how do we develop models that look like it, the brain, and maybe how do we make these models compact? So I think I'm going to try to address that one first. So what I would argue is that we are all contributing to the same cause and we're helping each other. So if you listen to the earlier talks, what you heard is people talking about these models that are convolutional neural networks for the most part. That's where their research resided. The reason is because up until about 2 years ago, those were the state-of-the-art models. And so we were trying to understand, how do these work? And how do we help them look more like what we would expect from a brain, where they're reasoning appropriately based on what we think about the way we think they should reason. So what we see, in my opinion, and I'm curious to hear from the speakers what happened. My opinion, what I hear is that they said, let's jump on the state of the art and figure out how to make these state of the art algorithms look more like how we want them to look. And my guess is they're going to now jump onto transformers and do a similar thing. And we heard from Miguel talking about how attention can be looked at different regions in these transformers. And so maybe that's a better model for us to mimic what's in the brain. And so I think that there's just like this natural marriage where right now, the people who are just saying, let's get statistical results that are good are sprinting ahead. And those that are trying to make it look like the brain are about following. But I suspect there's going to be a switch. Like I think there's this constant switch where we just help each other figure out, here's the new ingredient. And so maybe when someone figures out, here's the trick that's in the brain that these models aren't doing, then all of a sudden we'll get a big boost. And now everyone in the computer vision community will try to follow their lead, right? So that's kind of how I see this fitting in. And I do agree this would be a fabulous discussion topic with the other speakers. How do we make these compact? That's, I think, going to naturally happen, because when you figure out how to have these really intensive parameter rich models achieve something, there's often just a lot of noise in there. Like the extra parameters we found over and over just kind of distract from making the right prediction. And actually, when you distill down to the true essence of what is needed to make the prediction, you often actually get improved performance when you make these models more compact. So I think that that's just naturally going to happen when after we figure out how to make these clunky, massive things, how do we engineer it to be more refined to only include the ingredients that are needed?
Yeah, that's really fascinating. And I almost wonder if in our quest to make things compact, we actually do things that are more brain-like.
Me too. And yeah, I think a lot of us would be excited if that's how the direction went. I'm happy to answer the third question, but I'm also happy if we want to shift to the discussion at this point. It's really up to you as the moderator where you like to see us go.
That sounds great. Actually, we have come to the end of our official session time, but we had a number of technical delays, and I don't want to rob us of the discussion time. So I would like to invite those of you who need to use the restroom, stretch your legs, grab a coffee. You're not being rude if you want to get up and move around. There is coffee